Imagine you are handed a massive, chaotic pile of the universe's building blocks, raw, unrefined ores, gases, and crystals. How do you begin to sort them into any kind of logical order? The simplest, most practical answer is to divide them into two massive teams: metals and nonmetals. You do not need a deep background in chemical equations to do this. You can sort the vast majority of these elements simply by observing their physical properties. This textbook page outlines exactly how we do that. We are going to run these elements through a specific sequence of physical laboratory stress tests found in NCERT Activities 3.1 through 3.7 to see exactly how they behave under pressure. Understanding how an element reacts to a hammer or a flame dictates where we can actually use it in the real world. Our first trial tests surface appearance and hardness. We take sandpaper to the raw elements to scrub away surface impurities, and then we take a sharp knife to test their structural resistance. When you polish metals, they reveal a shiny, highly reflective surface known as metallic luster. Try to cut metals like iron or copper, and your blade will not make a dent. Physical profiles vary, even within the two teams. Sodium and potassium are metals, yet they can be sliced with a knife. Conversely, diamond, a form of non-metallic carbon, is the hardest natural substance we know. Next is the deformation test. We place an element on a heavy iron block and strike it repeatedly with a hammer. When a solid non-metal like coal or sulfur takes the hit, it instantly shatters into powder. This shattering is called brittleness. Metals react completely differently. Because of their unique atomic structure, the atomic layers of a metal can slide past each other without fracturing. Strike a piece of gold, and it flattens out into an incredibly thin sheet, a property known as malleability. This same structural flexibility gives metals another unique property, ductility. This is the ability to be stretched and drawn out into long, thin wires without snapping. If human civilization relied on brittle nonmetals, everything we build would crumble under load. The malleability and ductility of metals allow us to forge structural spans like this cast iron bridge, bearing massive weight without fracturing. This diagram illustrates our third trial, the energy test. We clamp a sample into a loop with a battery and bulb. When a metal completes the circuit, the bulb lights immediately. Metals are excellent conductors, allowing electrons and heat to flow freely. Nonmetals typically act as insulators, leaving the bulb dark. The standout contradiction is graphite, which allows electricity to flow as efficiently as many metals. Our fourth and final physical trial is the sound test. We strike our elements firmly against a hard surface to see how they propagate acoustic waves. Nonmetals absorb the kinetic energy and produce a dull thud. Metals exhibit a property called sonority. When struck, the brass in this school bell converts kinetic energy into vibrations, producing a deep, sustained ringing sound. A metal's ability to efficiently transfer invisible energy, whether it is propagating acoustic sound waves or carrying electrical current over vast distances, makes it the only viable choice for wiring and connecting our world. After running the gauntlet, we have a clear scorecard. Metals are generally shiny, hard, sonorous, malleable, ductile, and highly conductive solids, with high melting points. Nonmetals offer the exact opposite profile. They are dull, brittle, non-sonorous insulators. And while most metals are solid, nonmetals exist as solids, gases, and uniquely, in the case of bromine, as a liquid at room temperature. But as our laboratory tests showed, the physical rules of the universe are not absolute laws. The physical gauntlet has limits. It cannot reconcile liquid mercury behaving like a metal or the high conductivity of a nonmetal like graphite. While physical properties explain how we utilize these materials to build our daily lives, these contradictions prove that to truly classify the universe, we must look deeper than surface